thank you for joining us today. Welcome to the MTI Instruments webinar. My name is Kim Lloyd with MTI, and I'd like to introduce Director of Engineering Don Welch. But let me give you some info on Don before we get started. He got his start in telecommunications as an engineering manager of PBX development and joined MTI in 1984. When his hopes of being an astronomer were dashed in high school, he channeled his love for science into being an engineer with a focus on electricity and electronics in college. With that, here's Don.
Morning. Today we're talking about the 1510 signal generator, which is not just a signal generator, but also can simulate various different sensors. And what does a signal generator like the 1510 do? Although the specification sheet is about 2 pages, what I'd like to talk about here are some of the more important features of the signal generator, the 1510. One of the most important things is that it has a very precise voltage and charge signal output. And we're talking about accuracies down around 0.05%. It has dual digital synthesized channels. They're totally independent of each other, which means we can control them completely separate, although we can also synchronize them together. It has multiple different wave shapes. For example, sine, pulse, triangle. We can also generate TTL type signals, as well as charge and some other signals that are quite interesting. It's not an arbitrary function generator. You don't have to program it. It's just keystrokes to set up the common signals that you would ordinarily use for simulating sensors or testing systems or performing calibration. It's got a wide frequency range. It's basically down in the audio to ultrasonic, DC to 100 kilohertz. We have automatic sweep functions built in, so you can actually sweep the frequency response of an amplifier automatically. It has a jog function too to do it manually. There's 40 memory settings. If you have particular setups that you would like to keep, you can store those in memory locations so they're easy to recall. And they're non-volatile memory, so if the battery dies, they stay in there. It has a USB port. The MTI uses that to calibrate the instrument, and it can also be used to remotely control the signal generation. And of course, we're NIST traceable calibration, and we provide a calibration certificate with these sensors when we send them out. If we look at the top side of the 1510, we see that there's 4 connectors up there. There's basically 2 channels, but channel A, there's where you see volts there, is a BNC connector, which is a typical connector for connecting into systems, oscilloscopes, etc. We also have adapter cables available to go from that BNC connector to alligator clips or easy hooks. Just to the right of that, you'll see that there's a PCDE and a PCSE. Those are the charge outputs, and they're slave to channel A. The channel A connector is a MS3106 Type 10 Canon connector, which is fairly typical used in the industry to connect to charge amplifiers. A lot of charge amplifiers will have them made to this connector. And we also have a microdot connector, which is a single-ended output. I should mention that the Type 10 connector, the differential output, is actually fully differential, floating with respect to ground. And we have the channel B connector all the way over on the left over there. The next thing I want to point out is that we have soft keys. If you look just below the display, you'll see there's 4 buttons, and the functions of those keys change depending on where you are in the setup menu. This allows us to have a smaller keyboard, easy to use. You can actually use this keyboard with gloves on in freezing cold weather. What can the signal generator be used for? Actually, quite a few things. If we look at this chart here, we see some of the industries that the signal generator can be used in. Aviation and aerospace was what it was originally intended for. We've since found many, many more applications. Example, in energy, hydro, wind, in power generation plants. You have sensors, multiple sensors on the equipment in there, and data acquisition systems to monitor these. Transportation, automotive and rail. A number of railroad customers have used these for checking signals out in the field. Instrumentation and manufacturing and science-related industries also use it quite a bit. In medical, we have EKG, ECG type of signals are being set up with that because of the very low-level outputs of the 1510. Over at the left-hand side of this chart, if we look at some of the more typical applications, we can see that we can calibrate monitoring systems. As I mentioned, the signal generator has an extremely accurate output, so you can actually use it to calibrate data acquisition systems or to check to make sure that they're functioning correctly, and we'll have an example of that. Another important feature is that you can calibrate charge amplifiers and velocity probes. With the charge output from the signal generator, you can connect directly to a charge amplifier, verify the frequency response and its amplitude response with respect to frequency. You can simulate vibration signals and even create two phase different signals, asynchronous from each other, to simulate vibration conditions that may be found with rotating equipment. For example, in power generation, the large steam turbines or gas turbines. It can produce speed and tach signals, such as a magnetic speed pickup, which we have an example of, or an optical tach, which are also getting popular. It can be used as a signal source to check electronic systems, their bandwidth, and even the integrity of wires that are used in those systems. And of course, it was originally designed to check the performance of avionic vibration systems, and it's ideal for simulating the multiple outputs you get from a gas turbine engine. In our first example here, practical example, we're going to talk about simulating accelerometers. Accelerometers are used to measure vibration of rotating equipment, jet engines, pumps, generators, diesel, and gas engines. What this sensor does is it converts the acceleration portion of vibration signal into a picocoulomb per G output. And then typically what you have is a charge amplifier that's connected to this to convert that into a voltage. An example here is this Endevco part. This is kind of typically what you would find in the aviation industry, bolted to the side of a jet engine. Here we have a charge amplifier. This is called an MTI-41CA. It converts the charge picocoulombs per G output to a voltage. There's various different varieties of these out there. This one is a portable unit that's used in conjunction with balancing jet engines on the ramp or right at the airport. Quite often in power generation or machinery monitoring applications, you'll see smaller charge amplifiers that are bolted to the equipment close to where the accelerometer is located. And what we can do with the 1510 here, our signal generators, we can accurately check the calibration of this charge amplifier by simulating the accelerometer. In this slide here, we actually have the detailed steps that you would use to set up the signal generator so that it could simulate a typical accelerometer type output. And I'm not going to go through all the steps, but we can see that we're setting up a 100 picocoulomb charge. Once we set that up and we have the 100 picocoulomb charge set up, we would connect that 1510A over to the charge amplifier, which we saw in the previous slide. That in turn would produce a 1 millivolt per picocoulomb output. So those 100 picocoulomb charge output would turn into a 100 millivolt peak signal. And we would be able to read that either with an oscilloscope, a voltmeter, or a data acquisition system. So for example, you could go out in the field on the side of a piece of rotating equipment, disconnect your charge amplifier, connect this in place of it, and then check the integrity not only of your wiring, but the charge amplifier and the data acquisition system, so you could rather quickly check the integrity of a whole setup. And you can do it handheld, battery operated. You don't need to drag power cords with you, which can be difficult sometimes in large power plants. Another example we have here is a strain gauge. Strain gauges are used to measure stress and sometimes vibration in large structures and small structures too. For example, bridges can sometimes be outfitted with strain gauges so that you can determine if the bridge is weakening or beginning to fall apart. There's many other applications too where strain gauges are used. This little guy above, you see here, he's just 2 wires, but typically you find 2 of these things set up in parallel. One is to cancel the effect of the other in terms of voltage and aging. And these things are quite often connected as like a quarter bridge or a full bridge. What our signal generator can do is to simulate the output of this strain gauge. And these outputs are typically fairly small values that we're measuring. And we would use the bridge mode output of the 1510 signal generator to simulate these small millivolt outputs. And if you know what the sensitivity function of the strain gauge is, you can exactly simulate that to check that your subsequent system, process monitor or data acquisition system is correct. In the next slide, we're going to actually look at simulating the strain gauge and by way of a process meter. And what we're doing here is we're going to set the signal generator up to read a half a volt. Exactly, that's 0.5000 volts down to the exact millivolt. Note the process meter here, which is a commercial off-the-shelf meter that we were testing, reads 0.5016 volts. That's a 1.6 millivolt error. It should be reading 5,000. It's not. So we can see already that we have an error. Is it an offset or is it a gain error? Well, the next thing we do is we set our function generator, our signal generator, to 1 volt. Note the process meter here reads 3.3 millivolts error. So we can see that we have a gain error here of 0.34%. That can be quite significant if you're making very precise, accurate measurements. And that 0.34% is over the half volt range we tested. Of course, we could use the bigger range, but this is sufficient for this type of thing here. Now you could then subsequently correct the gain error in the panel meter by calibrating it. Or if it was just an offset error, if we read the same offset as we saw here, which was 1.6 millivolts, if we were only reading 1.6 millivolts here, we would know that was an offset error. But here we see we have a gain error. And these can be corrected once you know what those are. Another example is testing RPM meters. What we're seeing on this slide here is a typical magnetic speed pickup. There's a pole piece in here and a coil, and as the gear tooth rotates in front of it, produces a voltage output pulse. We can see the magnetic pickup here is placed fairly close proximity to the gear teeth, and these things generate a speed. It could be a once per rev or it could be a multiple per rev sinusoidal voltage pulse for each tooth encountered. A typical signal that you would see generated by this looks like this. These are positive going pulse as the tooth approaches the magnetic pickup, and then a negative going pulse as it moves away. The signal generator, the 1510, has 2 channels on it, and the B channel is actually optimized for producing tachometer type signals, although we could also use the A channel. So the example that we're showing here, a step-by-step setup of the 1510A on channel B, we're going to set up a pulse that's about a 10% duty cycle at 100 hertz, which would be the equivalent of 6,000 RPM. On the oscilloscope display, you can see the pulse's output there. So I could either have something that looks like a continuous sinusoidal or a pulse output. Once per rev output for tracking the speed of a machine kind of looks more like what you see in the oscilloscope there. So what we could then do is input this into our system to see what we read, if we're correctly reading the speed, if your time base and your data acquisition system is correct. It's a little difficult to see in this slide here. We've connected a tachometer up to a 1510. This is a self-powered tachometer, and we see that it's reading 6,000 RPMs exactly. So the time base here is very accurate. In the next example, I've set up another way to read RPM using channel A. And what we can do here is use the RPM function. If you look down a couple of bullets there, we're actually setting 100 RPM. So if you're feeling a little lazy and you don't want to calculate RPM, you can just directly enter RPMs via the keyboard. And we can see that the panel meter here is reading exactly 100 RPMs. So this little panel meter is pretty good. The 1510A can simulate quite a large variety of sensors, and it's not limited to what we're seeing on the slide here. I'm constantly surprised by applications that customers have come up with, and sometimes they call us and ask us how to do things. Feel free to question us if you have an application where you don't see it in our user's manual or here. We already took a look at accelerometers. We can simulate both charge and voltage output. Some accelerometers actually have a little amplifier built in, so it's voltage out, so you don't need the charge. Pressure transducers are typically voltage-type outputs. So what you would do is disconnect the pressure transducer from your system and then generate a voltage proportional to the pressure to check your system. We can simulate microphones, and you can actually use the sweep function in the signal generator to check the frequency response of an amplifier. Displacement measurement devices, a huge variety of displacement systems, one being LVDTs, and that produce a DC output or an AC output. You can simulate those also. Voltage generators. It doesn't produce power, but it can simulate frequency and voltage. For example, in aircrafts, they have tachometers that look actually more like a alternator or voltage output. We can simulate those where you check voltage versus speed. Tachometer speed pickups, we already saw an example of that with the magnetic pickup, and there's both commonly used today are magnetic and optical pickups. Servo control feedback systems. We have several people that have used this to actually help test servo control systems because of the high frequency response of our system here and the fact that we have two channels to be able to do that. Temperature devices. Thermocouples are very widely used, and how would you simulate that? Well, thermocouples, for example, type J or type K, thermocouples have charts where they show the temperature versus the voltage. So to test your system, you would connect the 1510 up, and you would set it, if you're trying to simulate a voltage, for example, of 100 volts, that might be 5.12 millivolts. So you would set the signal generator to generate 5.12 millivolts to make sure that the rest of your system is reading temperature correctly. For example, a process meter that converts that voltage into a temperature. Strain gauges, we saw an example of that. What's significant with our signal generator or signal simulator here is that we have bridge mode output, which is a very precise way of generating differential voltages down to the microvolt level, which will be important for the next two examples, EEG, ECG. The sensor signals that you pick up off the human body are very, very small, and they need to be precisely be able to be set. Another advantage for simulating these signals is that the 1510 is battery powered, so you can disconnect it from the AC mains, and that allows you to float the signal generator from the land-based power supply, 60, 50 cycles that you might pick up and mix in with the signals accidentally. Eddy current probe. With an eddy current probe, you need both AC and DC outputs. The DC is proportional to the sensor gap, for example, from a casing to a shaft. And then you have an AC signal when the shaft is rotating. So you can simulate both outputs from an eddy current probe. And we have a number of customers in the energy field that use the 1510 to simulate eddy current probes to make sure that the wiring and the signal conditioning equipment is working in the plant.
All right. Thank you, Don. Much appreciated. We're going to show a quick video while give you guys a chance to send some questions in. Remember that the Q&A window is in the lower section of the right-hand side of your presentation box. Feel free to ask some questions.
The 1510A can create a phase shift between its A and B outputs, such as may be encountered in a rotating system like a jet engine. It can also generate single or odd pulses on the bead channel to simulate tachometer pulses. These simulated signals generated by the 1510A can be used to test and calibrate charge amplifiers, which are used to condition the output of piezoelectric sensors. This is important as the signal response of charge amplifiers can change over time due to damage or natural drift. Periodic calibration is therefore necessary for accurate measurements. The MTI 1510A allows engineers to perform these calibrations in a controlled and repeatable way, whether in a facility or in the field. The 1510A can even be used for test and calibration of medical equipment. Its stable, accurate low-level signal generation is ideal for simulating the signals from EKG or EEG sensors.
The 1510A has, you have either a voltage output or a charge output, and you have different functions that control these voltages. So, for example, you can have a sine wave output, you can have a triangle wave output, you can have a pulse wave output, and there's also step functions that you can generate. And those signals you can control the frequency, you can sweep frequencies or jog the frequency to whatever you like. The voltages that it outputs are highly accurate and stable. The frequencies are very accurate and stable also. So you can actually use this to calibrate your signal conditioning equipment, whether it's an accelerometer or an eddy current. You can create various different signals that simulate those sensors to verify that your signal conditioning equipment is working. And this stuff can be out in the field where there's no external power source around that you could typically plug a standard signal generator into to simulate this. The 1510A, because it's battery operated, can be used out in the field or pretty much anywhere. It can be used in an airplane up in the air without having to connect to an external power source.
For more information about the 1510A from MTI Instruments, please visit.
Okay, so what we'll do is we'll open up the floor to questions. We'll take a couple. We want to keep this to a half an hour for everybody. So the first question that came in, one of the questions is, Don, is this really a portable device?
Absolutely. It's battery operated. Takes 4 AA batteries, rechargeable. But if you need extended periods of operation out in the field, you could always just pop the cover off and put more batteries in if you need to last longer. But it is a truly portable instrument. It's not tied to a tabletop power supply.
Okay. Are there any export restrictions?
No. Generally, export restrictions are tied to sensors that are measuring distances below 0.2 of a micron. There are no export restrictions on the 1510.
Okay. And then another question, can it trigger alarm thresholds?
Certainly. If you have alarm thresholds set in your data acquisition system, what you would do is set the 1510A up so that it's below the alarm threshold. For example, let's say you have an eddy current probe on a machine and you want alarm over a certain amount of vibration, say displacement of 3 mils. What you would do is set the equivalent, maybe 1 or 2 mils in the signal generator, and then jog that up using the manual jog function. And then as you go through that 3 mil alarm set threshold, you should see your alarms in your data acquisition system trigger. So you would be sweeping the amplitude or frequency, if it's a frequency alarm, past the alarm threshold.
Okay, great. So that's all the time we have for questions. I just want everybody to know that if there were questions that you weren't able to answer, or you just aren't sure at all if the product can work in your environment or with the purpose that you have in mind, please feel free to reach out. We have Don's email address there, and so he's obviously an expert in this area, so feel free to email him. There's also some more information on our website, so we are definitely looking forward to hearing from you. Thanks for joining us today.